Okay, then let's quickly return to our topic of BJT biasing. And I just want to quickly cover what we were talking about last time, the rules of thumb. And I want to point out, these are not hard and fast as in laws, but they're just good design recommendations. You may or may not be able to follow everything quite as explicitly. You may have to adjust some of these, but these are good starting points for a design. As we mentioned before, first of all is the rule of thirds, where VB is approximately 1/3 VCC and VC is approximately 2/3 VCC. As we mentioned before, that is a good compromise between dynamic range and also making the circuit insensitive to changes in delta VBE, or in the base emitter voltage due to temperature. And also, rule number 2 is that you should be somewhere in the range of 0.1 somewhere within the range. This current through this resistor should be somewhere in the range between 10% and 100% of IE. Again, because that reduces variations due to beta. So these are good starting points for a design. And I just want to mention to you, these starting points are going to become important to you later on in the lab. So I just want to kind of throw that out to you. There's a good reason why we use them, and as you're going to see, they make sense when we're doing designs. So I should also mention, I could also apply this rule of thumb up here, the rule of thirds, to a MOSFET, where I could say that VG is approximately 1/3 VDD, and VD is equal to approximately 2/3 VDD. So if I had a common emitter, or pardon me, a common source instead of a common emitter with VG and VD, I could apply that same rule. Because, of course, the threshold voltage can also vary with temperature. So this rule of thirds applies either to BJTs or to MOSFETs. All right? So good design practice, good starting points, but not hard and fast. You may not always necessarily be able to follow these guidelines, but they're good places to start when you're doing a design, if you want to get a design that's going to be robust. All right, so also just very quickly, just as with MOSFETs, we can do the same kind of biasing tricks with BJTs, and I just want to quickly sketch those. First of all, we can do what's called collector base resistor biasing, which is just like the drain gate resistor biasing we saw with MOSFET. Now the difference between this circuit and the MOSFET circuit is the current through that resistor is not going to be equal to 0. There is a base current you have to account for that's going to flow into the base. And so this will be the collector current. So the current through the resistor will actually be equal to the emitter current, because this current will be equal to IE is equal to IC plus IB. So this current and the emitter current are going to be the same thing when you think about it. KCL dictates that. And you can prove here in this case that IE, we can show that this is, that IE will be equal to VCC minus VBE. Of course, VBE is this voltage here in the circuit, the base emitter voltage, divided by RC plus RB divided by beta plus 1. So you can actually go through and prove that this is the correct equation to calculate that current. And you can also prove, although I'm not going to do it, that this circuit, just as with the collector gate bias circuit tends to be more resistant to biasing variations due to component parameters. All right? So you can use this. You can also, of course, use current source biasing. So just as before, with the MOSFETs, you can take a BJT and you can replace that emitter resistor with a current source. And once again, the current flowing through that BJT, the emitter current is going to be, of this transistor, is going to be set by however accurate the value is you can set for that current source. And what's that current source going to be? Well, you can replace that current source, the ideal current source, of course, with another transistor. And so I can simply take this and then put in a second transistor with its own bias network, its own emitter resistor, and I can go and set the current with that. But of course, all you're doing is you're pushing the accuracy issues over to that circuit too. So another way to do this is using the current mirror, just as we saw with the MOSFETs. So in this case, I'm going to have some current Iref, which is going to be set by my current source over here. I can generate Iref this way, or I can use a current mirror and generate Iref this way. So in lieu of a resistor, I can get more accurate and more stable biasing. And the current mirror technique, again, as we mentioned before, has a lot of advantages. In this case, these two transistors, Q1 and Q2, are matched. So whatever beta variations or what other parametric variations they have, if you manufacture them together side by side in the same process, those variations will track. And so in this case, again, they're sharing the same VBE. And that VBE, of course, appears up here. And so I'm going to have some I bias current, which is going to be equal to VCC minus VBE divided by R bias. The problem, of course, is I bias is not going to be the same as IC2. IC2 and IC1 will match, but I bias will not match because, of course, there is a base current. There are base currents flowing through these two transistors. And so that's going to create a small error between the two. But we'll come back later on when we talk about IC design, and we'll come back and we'll address this whole issue of current mirror design. So I just want to for now show you that you can build a current mirror with a BJT the same way as with a MOSFET. But we'll get into more details about how to build good current mirrors and better current mirrors, and we'll come back to all this later on. But for now, just want to make you aware that you can do it. All right? So questions about this? So finally, you can put all this together. And the book actually has a whole section on what it calls practical discrete amplifier design, where we kind of put all of these kinds of concepts together. And I just want to show a couple of examples. I'm not going to go over the whole section, but just going to point out how these circuits are going to look, and you should be able to analyze them yourself. So let's look at, for example, a practical discrete common source amplifier. So if you're going to go into the lab and you're going to build a good common source amplifier, one whose behavior you can predict, what's it going to look like? Well, something like this. So here we do a practical design. I'm using coupling capacitors to separate my load and my input source. And these C sub C capacitors will be large. And I want them to be big so that at AC, they're just going to be negligible impedance for any AC frequency we care about. But at DC, they block the flow of current, which means that therefore adding this and this to the circuit, the load and the input source, will not affect the bias of the transistor. So that's one of the nice things about capacitors. They let you separate the AC and DC domains from each other. Then you need to have something down here to help you set the bias. So what you're going to need down here is, and there are several ways you can do it. You can either have some type of source resistance, or you can replace that with some type of current source, like we've been talking about. So you can use one or more transistors to set that bias. So either way, you build a amplifier using one of those two schemes. And then finally, regardless of how you bias this, you also want to add a bypass capacitor. So CB is our bypass capacitor. And again, that's going to be large. So whatever element we put down here to help us stabilize the bias, we're just going to make sure that the source gets connected to ground so we get all of our AC gain. Makes the small signal analysis a lot simpler for us. So this is a practical design, something you go ahead and you build in the lab. Now you could take this and you could convert this to a common gate amplifier. I'll just switch to a different color here for a moment. I could take this same topology and convert it to a common gate amplifier just by moving the source. So in this case, I could do this. I could take the source and R sig, which is the Thevenin equivalent of my input source. I just ground that. Now the gate is now shorted to ground. There's no reason that it needs to be floating or anything. We'll just put it to AC ground. Makes for a more predictable common gate amplifier. Then I'm going to go down to this exact same circuit I did here. And that CB, that bypass capacitor, I'm going to lift up that bypass capacitor. And then I'm going to connect my signal source right here. So the same topology, just by flipping it around, I now have my common gate amplifier. So this is how you build these types of designs, okay? You got to make sure you use those coupling and bypass capacitors, and then figure out how you're going to do your biasing. Now if you look in the book, it's got a whole section where it covers practical common source, common gate, common drain, common emitter, common base, common collector. I'm not going to bother to go through those, but you want to take a quick look at them. I mean, you should be able to see that All we're doing is putting together these things we've already discussed. All right? Questions about this? All right. Let us now move on to a completely different topic. We're going to come back to amplifier designs later on. We're going to start talking about how we do IC designs, or how to do amplifier designs and integrated circuits. But for now, we're going to step back and spend the rest of this lecture talking about digital circuits. Now, first of all, I want to say to everybody, if you have not had digital systems, have no fear. This is not a digital systems lecture. All right? You don't need to know anything about digital logic, but I'm going to show you how digital logic works. When you took digital systems, those of you who've taken it, you learned about gates, right? NAND gates, NOR gates, inverters. But what's inside those gates? Well, let's talk about that, and let's also answer a couple of questions, which maybe you guys have considered, and maybe you never have, but now it's time to consider it. So let's talk about CMOS digital circuits. So we're jumping ahead a few chapters. And there are a couple of questions. Question number one, why are modern computers so much more powerful than they were 40 years ago? That's question number one. Guys, every one of you currently is probably carrying a smartphone that is more powerful than any supercomputer that existed on this planet back when I was your age in college. And every year, computers become more powerful and more capable. Why? Secondly, why have computers become faster? Why have clock speeds increased? So over that same span, 40 years or so, it actually goes back further than that. I'm just picking 40 years, okay? But I could also say 50, 60, from the dawn of computing. You know, 40, 50 years ago, a 10 megahertz clock speed was fast for a computer. I mean, I did my thesis work on a computer that clocked about that quickly, right? Nowadays, 3 gigahertz is, you know, typical. It's common. Your devices you're carrying in your pocket probably clock at 1 or 2 gigahertz easily. So we're talking about orders of magnitude faster clock speeds, which means they process information faster. Why has this happened? Well, that's a good question. Let's talk about that. And to understand that, we're going to look at the MOSFET as a switch, which is fundamentally different from everything we've been doing so far, because we've been thinking about, you know, a transistor is used as an amplifier. We forward it, we bias it in the saturation region for a MOSFET, for example. But now we're going to look at it, and we actually talked about this at the very beginning when we looked at MOSFETs. We're going to look at it when it's in triode. So, consider the MOSFET as a switch. Turns out, a MOSFET is a pretty good switch, a pretty good voltage-controlled switch. Let's consider this circuit. So looking at this circuit, we've analyzed this as an amplifier. It's a simple common source amplifier, but let's now kind of look at this thing from a large signal point of view, how this circuit's going to work. All right? Let's consider two cases where Vn is either 0 volts or Vn is equal to VDD. Let's look at the extremes. We're operating between the two power supply voltages. If Vn is equal to 0, what do I know is true about that MOSFET? It's off, right? MOSFET's off. Okay? If the MOSFET is off, then the drain current, which is flowing through that resistor, must be equal to 0. And therefore, there's no voltage drop across that resistor, and therefore Vout's equal to VDD. So we've already seen this. We've already talked about this before. Okay? Now, let's now assume that Vn is equal to VDD, and RD is large enough such that the transistor gets pushed into triode. So we'll be in triode operation. So in this case, if we're in triode operation, I'm going to think about this thing. I know it's on, but now I'm going to think about what's the resistance between the drain and the source. We talked about this before. We actually derived it. And so in this case, the conductance between the drain and source, I'm going to call this the on conductance for that MOSFET, will be equal to the change in the drain current with respect to the change in the drain source voltage biased in the triode region. And when we did this before, we derived what that would be. We took that derivative and we found that this was equal to K prime N times W over L times VGS minus VT minus VDS. So we derived that before. And that's the conductance. And given this conductance, we therefore know that R on is going to be equal to the inverse of that. Which will be approximately equal just to 1 over K prime N W over L times VGS minus VT if VDS is small. So we derived this before. You've seen this before. We derived this when we first started looking at MOSFETs in triode. So what I'm going to do is I'm going to take this R on and I'm going to replace that MOSFET that's been turned on with a resistor. And so what I'm going to get instead is this. And so I have this, V out. I've now got a resistor divider, right? So V out is just going to be equal to R on divided by R on plus VDD, or pardon me, plus RD, excuse me, multiplied by VDD. Now, if R on is small, what is that voltage going to be? It's going to be a small voltage. So if R on is much, much less than RD, then I'm going to have a voltage that's going to be something near 0 volts. In fact, we looked at this before. We sketched this kind of thing out. Remember? We sketched a voltage transfer curve of VDS versus VGS. And we saw it looked like this, where we started off in cutoff. We went through a saturation linear region, which we use for amplification, and then we wind down here in triode. So from a digital circuit point of view, I don't care about the linear amplification region. That's just a transitional region I'm going to pass through. I care about cutoff and triode. It's either on or it's off. Okay? Well, looking at this circuit, let's consider this from a digital logic point of view. Boolean logic. I'm going to say that the power supply voltage, VDD, is a logic 1. And ground, 0 volts, is a logic 0. So looking at how that circuit worked that I just drew, then if Vn is a logic 0, V out is a logic 1. If the transistor is off, V out is equal to VDD. And if Vn is a logic 1, then V out is, we call it a soft logic 0, approximately a logic 0. So it's a soft logic 0. It's not really all the way down to 0 volts, but it's going to be close enough. Close enough where a digital circuit will interpret it as a logic 0. So we look at this thing, and what is this logic function? Those of you who took digital systems, what is that? That's an inverter. Yeah, this is an inverter. Problem is, it's not a very good inverter. First of all, it's not what we call a hard logic 0. It's a soft logic 0. It's not quite at 0 volts. Also, during this soft logic 0, current is flowing through the circuit. ID is greater than 0, and it's dissipating power. Now you'll say, well, what's the big deal, Professor Holman? Yeah, I mean, so you're dissipating a little bit of power. Well, the big deal is I don't have one of these in a circuit. I have millions of those in a circuit. And if half of them approximately are dissipating power, that chip is going to be glowing red hot. You can't build good, reliable, practical logic using a transistor and a resistor. We had a name for this, and this was a big thing back in the 60s. It was called resistor-transistor logic. That was before we knew how to build good PFETs. So instead, there's a better way to make an inverter, and the better way is to replace RD with a PFET. CMOS inverter. In this case, I'm going to replace the resistor with a PFET, and both the PFET and the INFET are going to be connected to VN. Now, the trick to how this works is the way that PFETs and INFETs work. If I have a logic 1 at the input, what is the state of the INFET going to be if I've got a logic 1? Is that going to be on or off? It's going to be on, right? What about the PFET if I've got a logic 1? Well, in this case, the gate and the source of the PFET are connected together. VGS is equal to 0. So what's the state of the PFET? It's off. What if I've got a logic 0? Vn is equal to 0 volts. What's the state of the INFET? It's off. What's the state of the PFET? Well, now I've got a nice big VGS. VGS is equal to VSG is equal to VDD, in which case it's on. So notice the switching behavior is complementary between the PFET and the INFET. When one is on, the other is off. Okay? Which means your circuit's going to look like this. So when Vn is equal to 1 volt, or probably I should say when Vn is equal to logic 1, when it's equal to VDD, power supply. When Vn is equal to logic 1, then I'll have the following. And the PFET is off. Open circuit. There's no connection to VDD. All I have is a connection to ground. And so Vout is going to be equal to a logic 0. And in this case, it's a hard logic 0 because there's nothing but a resistor connecting it to ground. There's no current flowing through it. If Vn is a logic 0, in this case, the PFET will be on. Except this will be for the PFET. And I should also just add that this R on is for the INFET, just to clarify it. Here's Vout, and in this case, the INFET is off. So there's no connection to ground. The only connection is through a resistor to VDD. Therefore, Vout's equal to VDD. Vout is a logic 1. Now, what's nice about this is notice that when you're in either one of these states, no current is flowing through those two transistors. One is on and the other is off, but there's no path for current. And so you can hold a logic state without dissipating power, which is obviously really important when you're doing digital design and you want to make a power-efficient design. So this idea of complementary metal oxide semiconductors using INFETs and PFETs together in a complementary manner is absolutely fundamental to all modern design. Yeah?
Can you do this with BJTs?
You can do it with BJTs, but it doesn't work nearly as well, okay? Because you have to push the BJTs into saturation, which you don't want to do, okay? The equivalent of triode for an INFET is saturation for a BJT, which is very undesirable. It slows the circuit down. It doesn't work well. Now, people have done logic in BJTs. They use a technique called emitter couple logic. So it's not something we're going to cover in this class, but it's basically you can't build this kind of circuit and make it work efficiently with BJTs. Not to mention the fact that also when you're in saturation, current's still going to be flowing. Okay, because you can still have base current that's going to flow. And so again, it's not power efficient. But with a MOSFET, there's no gate current. You turn one on, you turn the other off. Yeah, ECL is actually, high performance bipolar logic design is a really fascinating topic, but I would need another class to teach you guys about that. So for now, we're just going to stick with CMOS and move on. Okay, so looking at all this, let's now consider something else. Let's look at this, and let's think about the way inverters work in a circuit. Let's now consider the output capacitance of a logic gate, and specifically this inverter. When you take an inverter and put it into a circuit, you've got to connect it to something else, right? You're connecting it to other logic gates, to other circuits. And therefore, you're going to have some equivalent capacitance loading the output of this inverter. So C sub L is going to be the intrinsic capacitance of the transistors combined with the input capacitance and the interconnect capacitance of anything it's connected to. So this is the intrinsic inverter capacitance plus the capacitance of any circuits that are connected to that inverter, right? Common sense. Everything's got capacitance. Well, if you think about it, I'm going to have one of these two circuits. And when I have one of these two circuits, the output node is going to be connected to a capacitor to ground. So I've got a resistor and a capacitor. What does that remind you of? Something from circuits 1? First order RC time constants, first order RC exponential rise and fall. Well, it turns out that is absolutely fundamental to what we're going to talk about. Let's go through a little thought experiment. So step 1. I'm going to assume a starting condition. I'm going to assume that in this case, Vn is equal to 0. The PFET's on, the NFET is off, and I'm going to assume that this capacitor C sub L is charged to VDD. So V out's equal to VDD, and this thing is completely charged. I'm starting with a steady state assumption, right? We know all about that. Steady state assumption. Okay, so now what I'm going to do next is I'm going to assume that I flip the input state of that transistor, of that inverter. So if I flip the input state, and I flip it to logic 1, then the PFET's going to turn off and the NFET's going to turn on. But, quick question. Can the voltage across that capacitor change instantaneously? Nope, we learned all about that. Voltages across capacitors cannot change instantaneously. So what's going to happen is the voltage across this capacitor, VCL, is going to transition from VDD to 0 volts. It's going to discharge. So I'm going to discharge to 0 volts through R on. So I'm assuming I instantly flip the state of the transistors, and now that capacitor charge is going to discharge. How long is that going to take? Well, not long. Okay, I like that answer. What is a more precise rule of thumb we learned about in Circuits 1? 5-tile rule of thumb, right? How long does it take to discharge within 1% of the final value? So, what we're going to find is here's V out. And once again, right out of 2112, V out is equal to VDD times e to the minus T over R on times CL volts. And it's going to take about 5 tau, where tau is equal to R on times CL to discharge according to that exponential equation. So we need about 5 tau to switch from logic 1 to logic 0. That's how long it's going to take that capacitor to discharge. Okay, now, next step is I'm now going to flip Vn back to 0 volts after this discharge process has completed. And then what am I going to have? Then I'm going to have my R on PFET now connected to a capacitor which is discharged, but now it's going to charge to VDD. Once again, exponentially. First order RC time constant. So in this case, CL now charges to VDD through R on PFET. What's the equation for that? In this case, this is V out. V out will be equal to VDD times 1 minus e to the minus T over R on times CL, where in this case the R on is for the PFET. And again, how long does it take for that process to complete? 5 tau. So it's going to require about 5 R on times CL for V out to switch from 0 back to 1. So let's imagine I keep doing this back and forth, flipping back and forth between those input states, and my circuit keeps inverting. Clearly, there is a fundamental physical limit to how long it takes for the inverter to respond to a change in the input. And that fundamental limit is dictated by resistance and capacitance. First order exponential response. Okay? So, let's consider a concept called feature size. Feature size, and sometimes you'll see it abbreviated as FS, is the minimum dimensions that you can manufacture a transistor with. And usually the number they'll give for feature size corresponds to the length of the gate. So the gate length is the number they use to specify a feature size. So over the past 40 years, okay, let's go back, for example, to, 1980 or thereabouts. So back then, back in 1980, you might, for example, have a 5 micron feature size. And that was a standard CMOS feature size in that range. 10 microns, 3 microns, but basically in those larger ranges is what you would see. And that was set by the minimum gate length of the transistor. Today, we're talking about gate lengths on the order of 6 nanometers. Thousands of times smaller. So, from back in 1980, all of the dimensions scale according to feature size. So for example, you might build a transistor that looks like this from the top. Well, here's the gate, here's the source, here's the drain, and your feature size would be dictated by that length. Except that now you can build transistors 6 nanometers, which means now my transistor looks like that. Actually, it's probably smaller than that. Okay? Everything is shrunk by a factor of 1,000. Today, guys, you can put an entire microprocessor in the area that was once taken up by a single transistor back when I was designing circuits. All right? Manufacturers have put billions of dollars into shrinking the sizes of the components. Modern fabs are constantly trying to make the components smaller. Why are they trying to do that? Let's look at that equation. As feature sizes shrink, the on resistances haven't changed that much. They've gotten a little bit better, but they haven't dramatically changed. But what about the load capacitance? What dictates capacitance? Well, let's think about that for a moment. Here we have a parallel plate capacitor. What dictates the capacitance? What is it proportional to? Area of the plates, right? The area of the plates. Okay. What is the capacitance of this versus that? Okay, this is literally, think about this. I am like essentially 3 orders of magnitude, but that's both in both dimensions. I'm 1,000 times smaller in length, but also 1,000 times smaller in width. So really, I am 10 to the 6th times smaller. So I can put literally 1 million transistors in the space where a single transistor went before. So that feature size works to the square, not just linearly, because it's both dimensions that are shrinking. It's just that we specify it in terms of the gate length, but all the dimensions shrink. Therefore, the capacitance C sub L decreases as the square of decreasing feature size. Okay, why are computers literally thousands of times faster today than they used to be. Right here. Because the taus are therefore much smaller. So they're much smaller. Literally millions of times smaller, thousands or millions of times smaller. Which means, since the maximum clock speed is dictated by those RC time constants, that means we can clock the transistors faster. Therefore, the inverters can be clocked faster. In fact, this answers two questions. Not only can we clock them faster, but why are computers so much more powerful than they used to be 30 or 40 years ago? Because now I can put 1,000,000 transistors where I used to have one. That's why you're all carrying supercomputers around in your pockets. Because we have gone to much, much smaller feature size processes. And every manufacturer is always trying to build the next generation smaller process. Because if you do that, you are literally going to have an enormous performance advantage over the competition. So this is why computers keep getting powerful, more powerful. This is why clock speeds have increased. But now let's ask one more final question here before we move on. How long does a battery in your laptop computer last, approximately?
4 hours.
About 4 hours, yeah. About 4 hours. Okay, so today, 4 hours for a laptop. Okay, 30 years ago, how long did a laptop battery last? You want to make a guess? I'm sorry?
It didn't.
Oh, it lasted. How long did it last? No, actually it lasted about 3 or 4 hours. Yeah. Believe me, I used them, guys, okay? I used those computers. Batteries lasted you about 3 to 4 hours. So I've been talking about all these enormous performance increases. But battery life seems to be about the same. Why? Let's consider that. Let us look once again at this switching behavior. And this leads to one of the fundamental design equations in digital design. Okay, if I am switching, if V out is switching from 0 to 1 with my PFET circuit, and I'm charging this to VDD, what is the energy stored in that capacitor? 2112 coming back to haunt you. 1/2 times CL VDD squared, right? The energy is equal to 1/2 CL VDD squared. 1/2 CVD squared. You guys remember that? Now, while I'm charging up that capacitor, current is flowing through this resistor, and that resistor is dissipating power. Anybody want to venture a guess how much energy gets dissipated by that resistor during that charging process? Exactly the same. You can prove it to yourself. R on dissipates. Also 1/2 CL times VDD squared during charging. So it turns out that charging that capacitor is 50% efficient. And incidentally, this is true regardless of the value of R on. It doesn't matter if it's large or small. You'll always dissipate as much energy as you actually store in the capacitor. Then let's go from 1 to 0. So now I've got my ohm resistor for the MOSFET, and now this voltage, this energy, 1/2 CL VDD squared, what happens to all that energy as this thing goes to logic 0? It's all dissipated in the resistor, right? Everything goes to 0. So as the load capacitance discharges, that stored 1/2 CL VDD squared gets dissipated. It gets dissipated in that resistor. So let me repeat this. I'm clocking this inverter. I'm flipping the input from 0 to 1. Every clock cycle, as I go through this process, how much energy gets dissipated each clock cycle, going from 0 to 1 and back again? CL VDD squared, right? So I dissipate half here, and then I dissipate the other half there in the other resistor during each half of the cycle. So this is dissipated every clock cycle. Okay, so let's sketch something out here. Here's my inverter. So I'm going to have my input and my output, and since they're it's an inversion, the input and the output are going to be inverses of each other. So this, of course, is logic 1, logic 0, logic 1, logic 0. Okay, so for every clock cycle, the energy dissipated is equal to CL VDD squared each cycle. All right, let's think about this. What is power? Power is energy per unit time. Fundamental physics. So I have a clock period. T is equal to the period of my clock. How long does it take to go through that complete cycle and then come back to its original starting point? So we all remember definitions of period and frequency. All right? Therefore, this must be equal to CL VDD squared per period. Right? A little bit of basic physics there. And what is frequency? Well, frequency is equal to the inverse of period. Right? Once again, basic definitions. And therefore, power must be equal to the frequency times the capacitance times VDD squared. That is the power that is dissipated by that inverter. Well, that's one logic gate. What if I have more than one logic gate? And on an integrated circuit, I'll have millions, if not billions, of logic gates. So for an IC with K gates, assuming all of them are switching at basically the same frequency, which is a assumption you can play with depending on what you can do as a designer. But assuming they're all switching at the same frequency, then the power of that IC will be equal to K times F times CL times VDD squared, where CL is the average output capacitance of any logic gate in the circuit. Okay, guys, this is the fundamental design equation that every person who designs every computer circuit in the world has to work under. This dictates what you can do, how much power you're going to dissipate, how much power you're going to need. Okay? So, let's think about this. As I shrink the feature size, then the capacitance area goes down as the square of feature size. So that basically shrinks as the square of that feature size. But at the same time, as I'm shrinking all the transistors, hey, I want to build a better product than my competition. So what do? I'm going to put more, since I can now cram more chips onto that die, or more transistors onto that die, I'm going to do it. So at the same time, K goes up because we want to add more functionality to the transistor. We want to make a better, faster computer. We want to add more memory. We want to add more processing cores to it. So the number of gates goes up. At the same time, as we shrink feature size, we shrink voltage because voltages get smaller, have become much smaller over the years. From 40 years ago, we went from 5 volts or 3.3 volts down to anywhere from like 0.8 volts to 1.2 volts. And again, this is a function of the fact we shrink those devices, the layers, the oxide layers get smaller. We have to reduce the operating voltages to keep from destroying the transistors. But we see as we reduce the power supply, we also decrease power as the square of the power supply voltage. At the same time, I also am very tempted to increase the clock speed. So clock speed tends to go up. So K gets bigger, the number of gates gets bigger, the frequency gets bigger, but the power supply voltage tends to drop. All of these things factor in the design you're trying to do as an engineer, as a designer. And your choices are going to dictate your power budget. And what is typically going to be the power budget that you are going to tolerate? Well, let's think about it. How long are you willing to tolerate a laptop working before you plug it in again? 3 or 4 hours. Manufacturers figured that out literally decades ago. How long are you willing to tolerate your cell phone operating on its battery before you have to plug it in? You want to carry it all day long, don't you? So that's a trick question, okay? Why does today the battery power of the battery life of a laptop the same as it was 30 years ago? Because the manufacturers know you'll put up with it, okay? Another factor that goes into here too is we have better battery chemistry nowadays. Lithium-ion batteries store a lot more energy than they used to. So all of these things factor in. So what engineers have to do is they decide what your operating lifetime is going to be, and they try to build the best and fastest systems they can within the envelope of that battery life. And then they will try to maximize performance by tweaking all of these parameters. So, again, cell phones last all day because nobody would buy a cell phone that only lasted for 2 hours. And laptop batteries last for 3 or 4 hours because long ago they figured out we're willing to live for that. So it's all a manufacturer choice. So I always kind of throw this in. There are some questions that are trick questions, and this is one of them. Okay? But everything is built within this parameter. All right? So Finally, there's one last topic I want to talk about. I did all this with inverters, but as you might guess, you can do this trick with MOSFETs and PFETs, INFETs and PFETs, with more complex logic gates. So once again, I'm going to test some people's knowledge. What if I showed you a circuit like this? What if I've got two inputs, V in A and V in B, and these are PFETs, and these are INFETs. And I'm going to assume V in A and V in B are digital inputs, logic 1, logic 0. I'm going to do something which you guys have probably, most of you guys hopefully have already seen, and we're going to do a truth table. Okay, let's look 0, 0, 0, 1, 1, 0, 1, 1. Let's look at all four possible combinations of V in A and V in B, and let's just consider them as digital logic. So if A and B are both 0, then the INFETs are both off. The PFETs are both on. What's the output going to be? It's going to be equal to 1. What if V in A is 0, V in B is 1? Well, I've still got this transistor on, and I've got one of these two in series off. So there's no connection to ground. There is a connection to VDD, and once again, I have a logic 1. Same thing if I flip the inputs, the A and B inputs. But if both of the V in A and V in B are 1, they're on, then both of those transistors are on. There's now a path from the output to ground. Both of those transistors are off, and I get a logic 0. So I'm just thinking about these transistors being turned on and off. And what's the path? Do I have a path to VDD or a path to ground? And there we go. What is this logic gate? It's an AND gate. What if I drew this? What if I did this circuit? And I kind of flip the topology around. And I did, once again, the same logic gate, or the same truth table, 0, 0, 0, 1, 1, 0, 1, 1, versus out. What do I get now? Once again, I can go through and figure out which ones are on, which are off. It turns out that in this case, unless both of these are off, or I should say only if both of these are off and both of these are on, do I have a connection to VDD, which gives me a logic 1. If either or both of these inputs are on, I have a path to ground. I have no path to VDD. What is that logic gate? It's a NOR, right? This is a NOR gate. Okay, guys, you now know more about logic gates than any computer science major ever will. Because you know what's on the inside. And not only that, you know why they work the way they do. Why does computer logic get faster and faster? Because of physics, because of RC time constants, because you guys took circuits 1. So you understand how the world works, okay? And you can still write software. But this really helps you understand. This is why digital logic works the way it does. Built within the constraints of that equation. And given any digital logic circuit like this, I can give you guys a truth table and just think about the PFETs and NFETs being on or off. You can trace the path and figure out what the logic is going to be. So you can build any arbitrary Boolean logic gate using transistors like this. Okay? All right. This wraps up all the information you're going to need for exam number 2. Okay? So next Tuesday, we're going to start on the final portion of the syllabus, but that is only going to be on the final exam. Okay? Yeah.
So the digital circuits that we were talking about today will be?
Absolutely. This will be. In fact, there are homework problems about it, and you're going to see problems like that on the practice test I'm going to post today as well. So it'll be there. But like I said, this is pretty fundamental stuff. If you remember your 2112, how this works is very straightforward.